Welcome back to Section 5, Uncertainty, Accuracy, and Precision. In this video, we're going to be talking about significant figures. This goes back to what I was talking about in earlier videos, magnitude versus number, the actual information contained in your measurement. So, the extra zeros that you can get in some measurements, they tell you about the size of the measurement, but they don't tell you about the actual value of the measurement. Okay, remember, I distinguished those as two different kinds of information. Significant figures are a way of counting, measuring the amount of information in the measurement, separate from the size of the number. So here, figure means we're talking about digits, the numerals, the numbers in the measurement, the individual numbers, like how 103 has a 1, a 0, and a 3. Okay, those are the figures we're talking about. And when we say significant, we mean that it contains actual information not related to the size of the number. Okay. So, some figures, some numerals are going to be significant, some are not. Some will always be significant, some will never be significant, and some sometimes. So here are the rules for determining whether a numeral in a measurement, whether a figure, is significant. Non-zero numbers are always significant. Okay? So you look at the number 37.8. That has 3 significant figures, 3 sig figs. Now, while we want to count sig figs, I'll get to that in a bit, don't worry. But non-zero numbers, always significant. Zeros are where things get complicated. There are 3 kinds of zeros in a measurement. Okay? They can be captive zeros, leading zeros, or trailing zeros. A captive zero is a zero in the middle of a number. It's been caught between 2 significant figures. Okay, so 102, 1 and 2, those are non-zero numbers. They are significant. The 0 is caught between them. It's caught between sig figs, so it is itself also significant. It is part of the actual measurement, is what that means. The 100 was part of the measurement, the 2 was part of the measurement, so the 0 in the middle, it's not just there to give you size, it's also information in the measurement. So it's a significant figure. Likewise, 10,002. The 1 is significant, the 2 is significant. The 3 zeros caught between them are also significant. So that is why we care about captive zeros. They're part of the actual measurement. They are there to give us information about the measurement. They're not just there to give us size. Leading zeros are never significant. The leading zero means we're looking at a number on the left-hand side of the number. They're never significant because they're only ever there to tell us about the size of the number. Okay, so 0.012. The 1 and the 2 are still significant, but those 2 leading zeros, they're only there to tell us that it's a very small number. They're not significant. They're not part of the measurement. Likewise, 0.00000000101 has 3 significant figures. The 2 1s are significant. The 0 that's caught between them, that's actually part of the measurement. All the other zeros, they're just there to tell us about the size. They're not significant. Finally, trailing zeros might be significant. That's where it gets difficult, because a trailing zero might be part of the measurement, or it might just be there to give us size. And the way we distinguish them is that a trailing zero is significant if it comes after the decimal place. So here, trailing means that the 0 is to the right of the number. Okay, so trailing zeros are significant only if they come after the decimal place. Okay, so we look at the number 1200, 1200. The 1 and the 2 are significant. The zeros are not significant. They're trailing zeros. They come before the decimal place. Then we look at 1200.00. The 1 and the 2 are significant. Those two zeros at the end, those trailing zeros after the decimal place. So they are significant. And then the other two zeros, they've become captive zeros caught between significant figures. Therefore, they are now also significant. So 1200.00, 6 significant figures. And then we have 0.001200. The 1 and the 2, again, significant. Those last two zeros, the trailing zeros, they are trailing zeros after the decimal place, so they're significant. But the other three zeros are leading zeros, so they're not significant. Okay? So 0.001200, 4 significant figures. So, to reiterate, we have different kinds of zeros because we need to distinguish between zeros that are part of the measurement and zeros that only tell us about the size of the number. Captive zeros are always part of the measurement. Leading zeros are always only there to tell us about size. Trailing zeros might be part of the measurement, might be there for size. That's why we have different rules for them. And now, an annoying exception. Something I kind of hate. I kind of hate it because it is so very, very easy to miss. This is what we do when we want to indicate that a trailing zero is significant before the decimal place. If you throw in a completely unnecessary decimal, that's how you indicate that that zero is significant. And that's why it's so easy to miss. It's the most insignificant. It's the smallest thing you can write. It's literally just a dot. It's so very easy to miss. And this sort of rule is going to become less important as scientific or exponential notation becomes more and more commonplace. But, progress happens one funeral at a time. There are still old people out there who use this rule, and they're still in charge, so you need to know this. When you want to show that a trailing zero before the decimal is important, you have an unnecessary decimal point. That's how you know it's significant. So you look here at the number 100, 100 dot. That dot, that decimal place, is completely unnecessary, and that's how you know that that final zero is significant. So now, the 1 is significant, that final 0 is significant, the 0 in the middle is now a captive 0, it's also significant. 100 dot has 3 significant figures. So, now that we can count significant figures, we can do math, using numbers that have different amounts of significant figures. Now, the reason we're doing this, like I said, is because we need to know how much information is contained in a measurement. When you're doing work in a lab, when you're taking measurements, you're taking different kinds of measurements, you're using different instruments, different devices to take those measurements, and you'll need to know how much actual information is contained in the result of the math you're doing. That's why we care about significant figures, because we're trying to keep track of how much information is really there, so that when you do various kinds of math, you know how much information is in your answer. Okay, where do you cut off the number, right? Where do you round? You do math with different measurements. Those measurements have different amounts of significant figures. How many significant figures will your answer have? That depends on the kind of math you're doing. We make the distinction between addition and subtraction on the one hand, multiplication and division on the other. Because when you're doing those two different kinds of math, addition and subtraction versus multiplication and division, you're transforming the measurements in different ways. So you care about the information in the measurements in different ways. Okay? So, addition and subtraction only ever takes place with the same kind of unit, and that unit has to have the same sort of prefix. Okay? So, when we're talking about significance here, what we care about is the number of decimal places. When you add a very significant, a very careful, a very precise measurement to a very sloppy measurement, okay, the very, very precise measurement, it can be the most wonderful measurement in the world, but if you're combining it with something sloppy, slapdash, and nobody gave a damn, then the sloppiness of the 1 amp measurement will completely wipe out the carefulness and precision of the other measurement. Okay, so precise plus sloppy, the result is going to be sloppy. Whereas precise plus precise, you can get precise. Okay, so that is how we measure significance and how we talk about significance when it comes to addition and subtraction. So the way you do addition and subtraction and keep track of your significant figures, you do addition and subtraction as normal. And then you start at the left and work your way right. When one of your two measurement runs out of sig figs, that's where you stop. That is going to be the limit of the precision in your answer. Okay, so now let's go ahead and work through an example. Here we have a perfectly normal addition problem. 13.8720 meters, nice and precise, 4 decimal places, plus 3.70 meters. Far less precise. It only goes down to the centimeter. Okay. So now, let's go ahead. We do our addition, 17.5720 meters. Let's find out where we're going to cut off our answer. Where does the information run out and the noise begin? So we start at the left, we work our way to the right. And we have the 1. Neither of our numbers has run out of sig figs, so we take another step to the right. Neither of our numbers has run out. Another step. Neither of our numbers has run out. Another step. Aha! Now, one of our numbers has run out of significant figures. It's run out of digits. That is where we're going to make our cutoff. That is the limit of the information in our answer. So that is where our answer gets cut off. Our less precise number only goes to 2 decimal places, so our answer can only go to 2 decimal places. That is the actual information contained in the result of our math. So when we're done, 17.57 meters. That is all the information we can actually get. And the reason for that is because, remember, when you take your measurement, that last decimal place is always an estimate. So the real number, the quote-unquote real measurement, that 3.70, it could be up to 3.74 or down to 3.66. You don't really know. Okay, so the extra decimal places and the much more precise number, that gets completely wiped out. Okay, we can't know. Okay, it's just lost in the noise. Multiplication and division is very, very different. Because with multiplication and division, you're combining units or eliminating units. You're coming up with a new kind of unit, a new kind of measurement. So it's not so much about decimal places. It's about the total number of significant figures. Okay. So when you do your multiplication and division, you do that as normal. Then you count the total number of significant figures in each measurement. Whichever one has fewer significant figures, that's how many significant figures your answer has. Okay. So it's just the total amount of information in the number rather than the number of decimal places. Okay. Addition and subtraction, it's about decimal places. Multiplication and division, it's just how many sig figs do you have. Here's an example. 13.2 meters per second multiplied by 0.82 seconds. We do our multiplication as normal, and here's our number, 10.824 meters. Now, how much information are we actually going to get to keep in our answer? 13.2, 3 sig figs. 0.82 has 2 sig figs. Okay, remember, leading 0, not significant. Okay, so, that 2, that's the smaller number. It has less information in that measurement. So that means our answer, our result, can only have 2 significant figures. Okay. So yeah, we're losing a little bit of information. We have 3 sig figs in our measurement of speed. We only have 2 sig figs in our measurement of time. So the result, the amount of distance we're getting out of this, is only going to have 2 sig figs. We're limited by the lesser amount of information. So we're going to have to cut it off right there. And our actual answer, we're going to round it 11 meters. So we're not really losing the information of the 0.824. We never really had that information to begin with. Okay, it only looked like we had that information. It's kind of an illusion. Now, rounding our numbers. We're not dealing with pure math here. Okay, this isn't this isn't math, or at least it's not mathematics. This is math as a tool in the toolkit of science. So we're not really dealing with numbers, we're dealing with measurements. And measurements are noisy, they're messy, they're rough around the edges. So that means when we do rounding with our measurements, we have to be clever, so that we make our measurements as good as possible, our math as good as possible, our results as good as possible. So rounding with significant figures is slightly different from rounding in pure math. When the number you're dropping is not 5, simple enough. Treat it as regular rounding. Okay? If it's above 5, you round up. If it's below 5, you round down. That's easy enough. Now, when you're dropping a 5, that's a little weird. Okay? Odd numbers will get rounded up to even. Even numbers will get rounded down to remain even. Okay, so 12.455 kilograms. We drop that last 5. We round 5 up to 6. But 0.08445 nanometers, when you drop that last 5, that 4 rounds down to 4. Okay, it stays even. That is kind of weird. But the reason we have to do that is because we're taking into account that our numbers are messy, and the people reading them, the measurements, the people taking down the numbers, have their own little quirks. Okay, we have found that people behave certain ways when they take measurements, and then they make estimates, and so we do this in order to get better results. It's a statistical technique, a way to make sure your numbers work out a little bit better. So there we have significant figures, significant math, significant rounding, working with significant numbers. How much information is there in a measurement? And when you combine measurements doing math, how much information will the result contain? And then, how do you round your answer? Okay. This seems kind of abstract, kind of weird, but I'm going to be a jerk about this when I grade homeworks and tests. I'm going to make sure you get the correct number of significant figures in your answer, and I'm going to make sure you get the right answer, that you do your rounding right. And finally, when are you supposed to round? When you're doing a complicated sort of math problem with multiple steps in it, how do you know when to cut off your sig figs? When do you do your rounding? You follow your PEMDAS. Remember, please excuse my dear Aunt Sally. Parentheses, exponents, multiplication, division, addition, and subtraction, right? And every time you switch to a different kind of math, that's when you that's when you do your rounding. Okay. So here we have a complex fraction, right? 13.05 plus 18.2 all over 12.01. So what that is an addition problem followed by a division problem. So you're going to do the addition first. Okay, 18.2 plus 13.05. The addition gets you just 31.27, but then significant figures, only one decimal place, so it becomes 31.3, and you do your rounding. Because now you're switching from the addition problem to the division problem. So 31.3 divided by 2.61. 31.3 has 3 sig figs, 12.01 has 4 sig figs, your answer has 3 sig figs. And the answer to this math problem is 2.61. So, whenever you switch from one kind of math problem to another, that is when you're going to do your rounding. Okay, and that will do it for significant figures. That'll do it for this portion of Section 5. See you next time.